In the last video, I've talked about Heisenberg's uncertainty principle, in which if we imagine thinking about the position and momentum of an electron, then the uncertainty of the electron position, delta x, times the uncertainty of its momentum, delta p, must be about equal to h, which is the Planck's constant. Now this result is closely connected to the wave property of the electron. In fact, we can actually, one way that we can understand it is by looking at some pictures, right? Looking at some pictures of waves and to think about how those can be used to represent the momentum and position of the electron. So that's what I'm going to talk about in this video. Now, let me just write out the uncertainty principle here at one corner. Delta x, delta p is about Planck's constant. Now, right. So first, let me look at p, the momentum. We remember from the Broglie's relation, p is equal to Planck's constant divided by the wavelength. So this is if we think of the electron particle as a wave with a certain wavelength lambda, then it would correspond to a momentum of p. Or if an electron has a certain momentum p, then it is like a wave with a wavelength, or in fact it is a wave with a wavelength lambda. That's the idea, and that has been actually confirmed experimentally by electron diffraction experiments, in which fringes are observed. So what it means is that I can think of an electron as a wave. It's a wave, and if this electron has a momentum p, has a certain momentum p with a certain value, then it must correspond to a certain wavelength lambda. So if it has a different momentum p, it must be a different lambda. Now, it is important at this point to realize something, which is that when we say that the electron is a wave with a wavelength lambda, or when we talk about a wave with a wavelength lambda, there is actually an assumption that comes with it. Right? The assumption is that we are supposed to think about this in a mathematical sense, which is that when we say a wave with a wavelength lambda, the understanding should be that this wave should go on forever. It should go on forever. The reason it should go on forever is that the idea of a wavelength is a repeating unit, and repeating in the sense that unless we say something else, right, repeating must mean that it just keep on repeating forever. Okay, so it's like when we talk about a straight line in mathematics. If we talk about a straight line in mathematics, it means that it's a line that goes on forever. Okay, so when we talk about a wave with a fixed wavelength, it means that the wavelength, the cycle, the period of the wave will just go on repeating forever. So it's an infinitely long wave. So this is actually the meaning that comes with it when we talk about when we use the Broglie's relation for an electron with a fixed momentum p, with a definite momentum p. Okay, there's all this meaning that comes with it, which is that not only does an electron with fixed momentum p have, not only does it have a wavelength lambda given by this relation, it also means that it is a wave, right, that is infinitely long, that extends forever. Now that is clearly quite hard to imagine from our everyday experience, because we are talking about a particle, which we think of it as just a small lump. Usually, if we think of an electron, we might think of it as just a tiny speck of particle, meaning almost zero distance. But here we are saying that an electron with fixed momentum is actually infinitely long. Okay. But that's the understanding from the theories and observations in quantum mechanics. And as I've said, that has been verified, at least to a large extent, by diffraction experiment, that electrons are waves. And right, so having said that, it also seems to suggest that if you look at an electron with a definite momentum, let's say we know that it has this momentum very accurately, then it means that it is an infinitely long wave with a fixed wavelength. Now, but if we look at this wave, let's think about the position. Look at this wave, and can we tell where the electron is on this wave? All right, from the wave alone, it does not look obvious whether the electron should be there or there or there. And that is simply because the wave looks the same everywhere. Right? Every peak, every wavelength of the wave looks just the same. And this seems to suggest that we have no idea. We have no idea where the electron is. Now, we can this observation, we can actually think of this as one of the first, if you like, one of the first application of the uncertainty principle, or we can think of it as one of the first example of the uncertainty principle. Because if I know the momentum definitely, that means that the uncertainty is zero in the momentum. There's no error or no uncertainty. I know that it's definitely p. Okay, so if I know that it's definitely p, then from this wave, as I've described, there's no way. Okay, there's no way we can be sure where the particle is, because the wave looks the same everywhere. Now, if you look at this uncertainty relation, you see that delta x times delta p must be equal to this fixed number h. So this also means that if delta p, if uncertainty in p is very small, then uncertainty in x must be very big. Okay, so that when they multiply together, you get back the same number. So in the extreme case, when the uncertainty in momentum goes to zero, then clearly the uncertainty in x has to go to infinity. So that means that the possible range of x is infinitely long. And it just means that we have no idea where the particle is, which is exactly as we would expect, as I've described, if you think of the electron as an infinitely long wave. So that seems to bear out, at least it seems to show that the uncertainty relation makes sense, at least in one way. Now let's look at let's look at this in a different way. How about if we want to think of the case when delta x is small, okay, meaning that here we have this example where we know the position very well, okay, but we have we have very little idea where the electron is. We have very little idea what is the x position. Now let's look at the other case where we know we have a better idea where the electron is. Let's say the electron is somewhere around here. What would the wave then look like? Now a way that can help us understand this is by drawing a few waves of different wavelengths. So let me try and do that. So suppose that I draw a wave of a shorter wavelength. Here. Wavelength, and I draw another wave, a shorter wavelength. So for this example, I've intentionally drawn it so that one of the crests or one of the peaks of all the waves are in the same position. Okay, so now I have these three waves. Now imagine adding these three waves up, like we do superposition in waves that I described in a much earlier video. So if we add all this up, then when the where all the peaks are in the same position, then let's say they are all, I've drawn them separately, but let's say I move them up so that they all overlap. They all happen at the same space. So where the peaks meet, they would interfere constructively. Where the peak meets the trough, right, they will cancel. Okay. Now as you can see, in this at least in this range of positions where I've drawn it, this center position is the only place where all the peaks meet. In other place, right, they don't meet exactly. Some peaks meet, but there are some troughs, or there are some sort of random parts of the wave at the same position. So this means that at other parts, away from this point, the waves would most likely cancel each other to some extent. So if I add this whole lot up, what I would expect to get is, I would expect to get a nice constructive interference at the center, but at other position, I would have destructive interference that might get worse and worse, as I move further out. So the wave, the resulting wave, when I add them up, would probably look like this. Okay, so it would have the biggest peak at the center, and as you move away, the peaks will get smaller and sort of more random. Okay, now if you look at this, it seems to it's like like a wave in which you have waves at the center, but you have less wave further away. So this seems to suggest that if you are talking about, say, if you're saying that this represents an electron, then the electron must be somewhere around there. All right. If you say that a wave, an electron is a wave, or this wave is an electron, then obviously where I have more wave, or wave with a bigger amplitude, that's where I have the electron, right? Where I have less wave, or where I have waves with small amplitude, I'm less likely to have electrons there. Okay, where maybe when it's further away, this might just say become 0. Then obviously there's no wave out there. If there's no wave out there, then there's no electron. So we have this idea that from this, this kind of idea, we can develop this understanding that the amplitude amplitude of the wave has something to do with the if you like, the chance of finding the particle there. Amplitude of the wave has something to do with the chance of finding a particle there. So I would have more to say about this idea later on, where we would try to make it a bit more definite and quantitative. But for now, let's just look at this as a qualitative idea. Okay, so where there is wave, there is electron. Where there's no wave, there's no electron. Okay, so that seems reasonable enough if we think that an electron is a wave. But if you look at this, part near the center, okay, we say that, okay, there is wave there, fine, so there is an electron there. But where? Where is the electron here? I mean, is it there or there? Where exactly is it? Because after all, the wave is a spread of wave over some distance in space. So actually, if this is all we have, if this is all we know about the electron, that is this spread of wave over this small region in space, then the answer is simple. We won't know exactly where it is down here, but we would know that it is somewhere within this range of delta x. Okay, and that is the uncertainty, and that is the uncertainty in the uncertainty relation from Heisenberg. So we have this range of uncertainty in the position. But if you compare it with my first example, in which I have a definite momentum and the wave just stretch on and on until infinity, looking exactly the same everywhere. Right? In this first example, I have no idea where the x is. It can be anywhere. So in this first example, delta x is infinity. Okay, but at least here is better. Here I know that the electron must be within this much smaller range of delta x, and not just anywhere at all. Okay, so here at least I have a smaller range of x, I have a smaller uncertainty. I know roughly that the electron is here. So I know something about the position. So I have a smaller delta x here. But according to the uncertainty principle, if x is smaller, delta p must be larger. So let's look at the delta p for this. What is the delta p? What does it mean, the delta p for this thing? Now let's look back at how this thing, this pulse or blob or bunch of waves, or however we like to describe it. Let's look at how this came about. Now, it came about by me adding together a few waves of different wavelengths. Now, remember that I was saying wavelength is related to momentum by de Broglie's relation. So when I had a definite p, I had a definite wavelength and an infinitely long wave. So in this case, if I have a few different wavelengths, it means that I have a few different momentum. So for example, for this wavelength, maybe it's a shorter wavelength, so I have lambda, maybe lambda 2, and my wavelength might be p2. For my momentum might be p2. It would be given by a different p according to this relation if I have a different wavelength. And for this one, I have an even shorter wavelength, say lambda 3. So the momentum p must again be given by a different value. I'll call it p3. So in other words, if I have such a wave like this, it must be made up of a number of different momentums. Right? I can only get this wave if I add up waves of different wavelengths. Right? Otherwise, for a single wavelength, it would look like that. So if I have to add up waves of different wavelengths, it means that I have to combine a number of different momenta together. So in other words, in this wave is a combination of a few different momentum. So this means that, you know, I have this combinations of all this range of p. So p P2, P3, and I can imagine adding more. Okay, so if I think of this as a range of momentum, I'll call it delta P. So I need a range of momentum in order to make this possible. Like I said, if there's just a single momentum, it would just be an infinitely long wave. So in order to reduce, to know the position more definitely, in order that we have a more definite position of the electron, that the electron is, if you like, localized within a smaller range of a smaller distance in space, it must contain a much wider range of momentum. And what we have here is a description in which we have, it is as if we are saying that for this electron to be here, it must have a number of different momentums, or in fact many different momentums at the same time. Now this in itself is a very strange idea, because if you look at say a piece of rock in your hand, alright, it is there in your hand, it has a fixed position, and if it's moving, it can have a fixed speed. So how can a lump of rock in your hand has a number of different speeds or different momentum at the same time? Now, in everyday experience, that is not believable. That is incredible. But in the world of electrons, this effect becomes quite obvious. At least the observation that seems to result from this understanding, like all the things about difficulties in measuring positions and uncertainties in momentum, when we try to measure it, it becomes quite obvious that that if we think of an electron in a certain range of position that we know is in a certain range of position, then it must actually be made up of a range of different momenta at the same time. And I shan't go into this the details of this in very much more for this video. Maybe a bit in a later video I'll show some more examples on how this works. But for now, let me just finish off by mentioning something called the Schrödinger's cat. The Schrödinger's cat. Now, the Schrödinger's cat is an example which is made up by Schrödinger, by Erwin Schrödinger, who is very important for the wave functions I'll talk about later. And it's an example made up by Schrödinger to show how impossible and ridiculous this idea of having different momenta, for example, at the same time is. Now, Schrödinger's cat is a cat in a box. Right, this cat in the box, right, when we put the cat in a box, and of course at first it's alive, and then there is hanging from the top of the box, there's a tube of deadly poison. Right, there's a tube of deadly poison, and perhaps at any time the cat might just knock the poison, which would then spill out and kill the cats. Okay, so while the cat is still alive, we close the box so that we can't see the cat. Now, the moment we close the box, you have no idea whether the cat is dead or alive until you open the box again. So as long as you don't open the box, there is the possibility that the cat is alive. There's also the possibility that the cat is dead. Now, from the understanding of quantum mechanics, that means like the idea that, for a rock or an electron, it must have different momenta existing at the same time. It's like saying that Schrödinger's cat is both dead and alive at the same time. And Schrödinger wanted to use this example to show that this must be wrong. It can't be right. But even until today, people are still arguing about what is right.